Hello everyone, I'm Abu Bakr, joined by Will, Sarah, and Ireland. We're the Motion Lab team. Our team was tasked by the sponsor, University of Rochester Medicine Motion Analysis Laboratory, to engineer and develop a prototype of an integrated harness with load cells and amplifiers, as well as modifying and improving other components such as floor coverings and safety mechanism that the lab was already implementing. The Motion Lab uses a perturbation device, which is a piece of exercise or rehabilitation equipment and specifically designed to apply controlled destabilizing forces to a person's body to challenge and improve balance and also improve their stability in reactive postural control. And this device is used to stimulate real-world balance challenges and enhance neuromuscular responses. The University of Rochester Medicine Motion Analysis Laboratory studies the kinematics of human motion and develops experiments and therapies to help understand stability and to improve movement. This project includes hardware that is designed to safely trip a user so that their ability to recover can be safely measured and improved. It has also been developed to replicate slip-like disturbances during gait, provide an objective platform to study neuromechanical responses and stability. The system integrates strain gauges and feedbacks, and it enables precise multidirectional forces and is implemented alongside treadmill motion captures and force plates.
Controlled perturbations allow measurement of response timing and joint loading patterns. This approach offers surgeons, physical therapists, and rehabilitation specialists actual insight to identify deficits in balance control, guide individualized post-injury rehabilitation, and implement targeted interventions aimed at restoring functional gait and reducing fall risk in patient populations. There are aspects of this device that have already been implemented in the lab and other items needing a lot more improvement before it can be used by the patients. The patients using this device will likely have concussions, are recovering from surgeries, or will have other mobility issues. So it is essential that this device is safe and comfortable in addition to its functionality. By improving their system and implementing our ideas, using the perturbation device will be more efficient for both the healthcare provider and the patient. It is necessary that patients seeking help from the Motion Lab can receive effective care. And so by making a device that is more streamlined, more robust, and safer, the lab will be able to see more patients and in the end, help more people. At the end of the semester, the final deliverables we will be giving the Motion Lab include a functional prototype, a technical report with test data, and a theory of operations manual. To ensure the correct design and success of the project, certain requirements are defined in consultation with the customer. These include mounting plates in the frame must be aligned, harness must fit the 5th to 95th percentile of male and female body types in the US and still be able to measure patients at the hip for the motion trackers. Packaging for load cell wires will be clean and will not interfere with tension of paracord. Device must be able to disturb gait and catch a fall safely. Prototype must be designed robustly for continuous everyday use, and patients must be able to be pulled in the cardinal and ordinal directions. To design and build prototypes to meet these requirements, certain specifications were determined. These include designing and bulk items will have a factor of safety of at least 2. Everything must maintain functionality when the treadmill is inclined to 9 degrees, which is the max angle it can go. The adjustment increments for the height adjustment of the pulleys will be no greater than 2 inches. The harness will allow for adjustment such that the angle of the patient's knee does not go past 90 degrees, and the frame will be able to be set up by no more than 2 able-bodied people.
As part of our functional prototype, we had to select a harness that met the requirements of the Motion Lab. And we did that via concept selection via the selection matrix seen in the top right. Each concept represents each team member's idea for the waist harness solution. After meeting with Zach, the motion engineer, and talking through all the ideas, the team decided to combine specific parts of several ideas to ensure the maximum safety and comfort of the patient. And our final design is listed as idea 5 in the selection matrix and can be seen right here on the bottom of the slide. However, this idea ranked lower than or tied with some of the other ideas in the most important categories, including adjustable for all sizes, accessibility of amplifiers, time to implement, cost, and safety, but it still had the highest total and weighted total in the matrix and was the safest by far. Combining the harness with the strap on the pouch allowed for the load cells, amplifiers, and NI device to be attached directly to the patient, which decreases the number of cords and wires that needed to be wired to the patient from outside the frame assembly. Some of the harness criteria included the waist size ranges, um, from the 5th to 95th percentile. It could still attach the paracord wire to the waist of the harness and could attach the load cell amplifiers to the harness and also could attach the safety cord to the harness. Ultimately, not all these requirements could be met with a single harness, which is why the team decided to use Motion Lab's existing shoulder harness to attach the safety cords. It didn't work to attach the pouch, load cells, and amplifiers, but it worked well to attach the safety cords because of the loops on the shoulders. So a pouch was purchased to clip onto the waist, harness to house the amplifiers.
The original frame did not align with the floor's permanent mounting posts, and this created a problem. Multiple designs, such as socket joints and clamps, or using a hollow mounting post, or using existing frame and customizing it was proposed. And a selection matrix was used in order to find the best idea. The winner was a suggestion from our Motion Lab engineer, Zach, and the idea was to use upward-facing bolts with cone-shaped tips to act as locators, and it outperformed other ideas in terms of speed, implementation, and safety. The existing bolts were modified and cut into the cone-shaped tips. The system is now fully implemented and includes floor covering to eliminate to eliminate tripping hazards when the frame is removed.
All right, so for some further analysis, we did some tolerance and fatigue analyses, one with the 3D printed corner calibration marker plates and the other with the eye bolt connection with the load cells. We will get into exactly what these do in a little bit, but for the 3D printed marker plate, the purpose of this analysis is to determine how far the motion tracker calibration balls can deviate from their nominal position when they are in their respective pockets or pegs. Because the pegs in the bottom here are a little smaller than the holes that they go into, so there's a little wiggle room. They can either translate or they can rotate. And then in addition, you add that to the inside here. I can show down up here where the bases of the corner or the bases of the calibration balls can also wiggle around in here just for clearance. And you add those all up with the given plus minus 1 millimeter tolerance range from the Motion Lab. The worst case calculation is plus minus 0.789 millimeters. So this confirms that we are properly within our tolerance range. Moving on to the fatigue analysis. I'm going to move our faces. We analyzed the pull between the load cell here, the threaded load cell, and then the eye bolt. And so the way we did that, a few key assumptions had to be made. We said that the maximum pull force is about 10 kilogram force. And this is a conservative estimate, and since when it is in the system, there is always at least a little tension with the motors. We're going to say the minimum force that is on this is about 1 kilogram force, and both of these are assumed to be made of 304 stainless steel. So essentially, what we did first is we calculated the max and min stress based on the areas of this, and then we calculated the mid-range and the average stress. And then from there, we plugged that into the endurance limit estimate. And then we took that estimate and used an equation from Muir's lecture slides, where we find the actual endurance limit with things like size factor, reliability factor. It's K, A through F. Once we did that, we plugged it into the modified Goodman and Solarberg criterion, and both of these values were far less than 1, which indicates that the system will have an infinite life and that there is no failure point with the pulls. And something to note too is we assumed that the cycle count would be about 100,000. This was a sort of an arbitrary estimate, but regardless, infinite life.
So we also conducted a fastener torque analysis and a statics analysis for our system. So verifying that bolted connections are torqued properly is critical to ensure safety in an assembly. So by finding the proper bolt torque for these connections, it's certain that the bolt will remain in place. For this, we analyzed quarter 22-inch bolts made of 304 stainless steel that are zinc coated. These bolts are located at the bottom of the frame to attach to the plywood so that for design day, the frame will remain in place on top of the plywood. So using the equations in our lecture notes and in Shigley's, the proper bolt torque was calculated to be 2.98 pound-feet. For the statics analysis, to verify our factor of safety, we calculated the max force the safety cords and harness would be subjected to if a 95th percentile male were to fall in the system. This analysis analyzed the maximum tension experienced by the two supporting ropes in the event of a fall. These calculations can be seen to the right. So based on these calculations, each rope must hold 1,250 pound force. And with that factor of safety, the ropes that we purchased can withstand 2,500 pounds force.
We also performed an FEA on the frame we created for design day. So as you can see on the left here, this is our finite element model, where the green mesh or the green members represent the aluminum tubes and the red members represent the paracord cross bracing. So all of these members are represented as C-beam elements, where the aluminum ones have tube cross sections, and the red ones have rod cross sections based on measurements we took of the tubing and the paracords. Um, the C-beams were used for this analysis due to the minimal curvature in each part. Also, each cross section was consistent along the length, and the cross sections are very small compared to the length of each member. Also, an element size of 6 inches was used for all geometry because each metal tube and paracord wire was at least 3 feet long. We also have an applied load here represented by these red arrows. That's the 2,500 pound force that we talked about in the statics analysis, and that's split between two locations to represent where the safety cords would attach to the harness. As we said before, the 2,500 pound force is the maximum force that the frame would be seeing based on our requirement of using the 95th percentile body type in the US. Additionally, the four legs down here are fixed in all directions. So if you look to the right, you can see our linear statics results of the finite element model. Um, the left one up here in the linear statics results displays the magnitude of the nodal's displacement in the frame, and then the right displays the stress. And as you can see, the max stress is less than 2 inches, despite the fact that we're applying a really, really high force. And then the bottom here is our linear buckling solution, um, where, as you can see, the high stress is actually in the paracords, which would actually go slack and not buckle, because, they're paracords and they're not like metal bars. And we decided to show this because initially we had a buckling issue with one of our rods at the top here. So we just wanted to show that it would be that paracord that would go first and not the aluminum rod at the top. Additionally, we used von Mises stress for this analysis since the material is ductile. And because the material is ductile, von Mises is the appropriate stress to evaluate.
In terms of manufacturing the guide bolts and
Yeah, I think it's me.
you skipped the
Did I skip? I don't think so.
oh, I meant go ahead.
Okay. All right. So here is some of our manufacturing. This is everything that we 3D printed. Starting it off with the corner calibration plates, which I already spoke of in the tolerance analysis. Here we have the very creatively named front right, back left, and this one is the front left, but The reason that there's sort of a hole cut out in the middle here is in the motion lab, there are two screws that we have tried our best to take off, and they don't sit flush with exactly where the plates go. And so we cut our losses and just basically went around. Doesn't change how it works, just a little different. They're 5 by 1.13 by 0.145 inches, and this is accounted for vertically in the offset when you calibrate the tracker balls, and they're only 30% infill because they don't actually carry any stress, so they can be quite weak. Next, we have the motor spools, and these attach the motor shaft and then wind the paracord, and they have a 14.1 millimeter internal diameter to fit around a 14 millimeter motor shaft, and a little key here was cut in the spool, and then a key way was cut in the model, and then a key was placed in here to sort of lock it in. And then here we can see 3 holes put into one side to tie the end of the paracord, just a little quality of life and housekeeping upgrade. And then per the Motion Labs request, they are 100% infill. Originally, I had printed them with 50% infill, but during testing, they snapped in half right along here. So they wanted them completely solid. And then finally, we have what we call the amplifier boats. And these boats are placed in the fanny pack to basically provide strain relief on some of the wires coming out of the amplifiers. And so they're a little curved at the end here. And this makes it so the wires just can't bend immediately upon coming out of the amplifiers. And they all sit in their own little respective parts of the pouch. So once again, just a little safety thing.
So, in terms of manufacturing the guide bolts, they were the team's solution to the frame alignment issues. And these bolts would allow the frame to be mounted and bolted with less efforts. And to kit the guide bolts, a 1/4 inch bolts were modified so that the holes in the frame could easily slide into the bolts. And using the belt sander, about a 1/4 inch of the bolt length was shaped into a cone. And the result was a bolt with the point at the threaded end, and this would help the frame slide easily into its place. And only 2 out of the 4 holes on each mounting plate had guided bolts. The other 2 were used to bolt the frame down. Additionally, floor coverings were manufactured to prevent anyone in the space from stepping directly onto the exposed bolts and injuring themselves. And the holes in the floor in the spiked guided bolts created a hazard for everyone in the space. And the solution to this was to create floor covers out of plywood. And the holes in the plywood were measured, and the plywood was cut accordingly to fit the hole. And the table saw was used to cut the plywood into the required shape, and holes were cut into the floor covers to fit the guide bolts. And a handheld drill was used with a 1/2 inch bit in order to create these holes. And the rectangular hole in the middle of the floor is used as a handle to pick up the covers when the frame is needed to be set in place or taken off. And a handheld drill was used to make the holes where the 4 corners of the rectangle would be, and then a handheld jigsaw was used to cut out the rest of the rectangle.
So we also had to deal with some cable management and organization in order to deliver an even higher quality functional prototype to the Motion Lab. So we have this pouch that connects to the waist harness, in which the amplifiers, the breadboards, or the breadboard and the excess load cell wiring will be housed. That's in the main pocket of the pouch, and then in a side pocket, the NI data acquisition device will just rest there. And then we also had some color coding of the wires, so it's clear which wires go to which amplifier and load cell. And then we were also able to replace some unnecessary banana cables with soldered breadboard. And then we were also able to extend a wire of the 10-volt power supply so that it could reach the harness while being plugged into the wall. Additionally, we put grommets into the pouch, which will just allow the wiring to pass in and out of without having to open the zipper. And yeah, we also put grommets into the front and main pouch so that the wires could reach the NI data acquisition device.
So for our wiring diagram, the left image is the overall wiring diagram. You can see that the wiring goes up from the power, up and over the frame to the harness, and then back down to the computer. And the right image is a more detailed wiring diagram that's happening inside the harness that you could see on the previous slide. This includes 4 load cells, 4 amplifiers, a breadboard, an NI DAC, and the wires connecting them. The way that this was wired, we were able to get rid of some of the wiring that was connecting to the patient originally, just having a more streamlined solution for the lab.
So here we have our design day frame. We were unfortunately unable to use the frame from the Motion Lab, so the best option we had was to build our own. And so we used extra aluminum tubing from the Motion Lab, which they used to hook up their motion tracking cameras. And the frame is 3 feet by 4 feet by 7 feet tall. And as you can see here, we have T-joints, and then we also have 4-way joints that connect everything up, also provided by the Motion Lab. And then originally it was spoken about a little bit earlier, but these 2 feet tubes that summed together to get the 4-foot tubes were cut into two. And there was a little problem with buckling. When we would pull down on the main supporter, we experienced a little bending. So what we ended up doing was just having extra aluminum tubing, and we just cut just 2 4-foot, and then problem solved. And so the frame is bolted to a 5-foot by 4-foot sheet of plywood painted black, just so it looks nice. And then there's a rubber mat, it's kind of hard to tell, under the plywood, just one to protect the floor of the GAC where we're presenting, and so it doesn't slide around. We also have the walking pad here to simulate the treadmill at the Motion Lab. The treadmill at the Motion Lab, as seen previously, is a little wider, so this is the best thing that we had. And then one thing to note is the cross bracing here. This was a preliminary test with the tension of it, and so we essentially just taped the paracords to the frame. Now we have a far better method of doing it. Unfortunately not pictured here, but where we attach the paracord to the clamps that hold the pulleys that hold the other paracords that go to the frame.
So here is just our final CAD model and drawing that shows the whole system, and then also the real life version we took during our testing of all of our devices.
In terms of the testing of specifications, the specifications were determined by consulting the sponsors as well as the professor, and they were agreed upon at the beginning of the project, in the beginning of the semester. And all designed and manufactured components in direct contact with the patients were required to have a factor of safety at least 2. And other specifications included the device to have functionality when the treadmill is inclined to 90 degrees, because that's the maximum angle that the treadmill can tilt. And the height variability for adjusting the clamps on the frame must be adjustable in increments of 2 inches or less. And also, it was required that the system will allow for adjustments so the angle of a patient's knee is not less than 90 degrees if they fall during perturbation. And finally, the frame must be able to be set up by no more than 2 able-bodied people. And all these specifications were tested by connecting a team member to the entire completed system at the Motion Lab. And the system was also tested, and the requirements and specifications were verified in the presence of a representative of the Motion Lab.
So here we have the MATLAB code that we are, or the MATLAB code output that we are using for design day. The code originally started by using the Motion Labs MATLAB code, and it was heavily modified. The Motion Labs MATLAB code had only the force over time plots and for each load cell, and so we changed it so that we can have a net force direction, which we thought would be pretty cool, because when someone is pulled, you can see the exact direction and the magnitude of the force that they're pulling with. In this image, we see the northwest and northeast load cells are being pulled, That's why they are that's why they're up here. And then you can see the corresponding arrowhead. As you can see here, it's about four kilogram force, and here we have about two. And so it's going to pull more towards the northwest side. Also important to note that the arrow increases and decreases with the magnitude of the pull, as well as changes color, just as a little cool thing that we added.
Given more time, we could have done a little bit more with the VR. We could have helped the motion lab further immerse their patients by providing an environment with obstacles in VR that could track the patient's full body movement in addition to their hands, which they already have done. Maybe we could do something with their feet. And then in terms of design day, we could have implemented the motion trackers as well if we had time, and if they let us have access to their VR or their motion tracking cameras too, we could have done this. Um, Additionally, we could have come up with a more efficient solution for the frame alignment. Currently, the guide bolt solution works just fine, but it still does take at least like 5 minutes with a couple people. So there could be ways to improve that. And then we would also like to improve the cable management within the pouch. Although the color coding does help, due to the size of the pouch, the wires are packed in pretty tight, so we would definitely improve on the packaging within that pouch. And finally, we would like to acknowledge the Motion Lab, including Zach Farnham, Dr. Ram Hadas, and Dr. Wood, and Brian Morey. And then we would also like to acknowledge the Mechanical Engineering Department at the University of Rochester, including our professor, Christopher Muir, Jim Elkins, Chris Pratt, Sam Kriegsman, and our TA, Liz Martin. So thank you for tuning into our presentation.